Good afternoon. My name is Luke Avaya. I'm here representing CMC Microsystems, a Canadian not-for-profit, and our mission is to accelerate the adoption and commercialization of advanced technologies like quantum. So I'm very happy to be here moderating this panel on From Discovery to Deployment, Scaling Quantum Beyond the Lab. And I'm joined by a series of esteemed guests who I will give now the chance to introduce themselves and their organization, take 1 to 2 minutes, and starting with Jestin.
Hi, everyone. I'm Jestin Huneault. I'm with Yoann Systems. We build universal gate-based quantum computers that rely on superconducting qubit technology. A defining feature of Yoann is that we're a vertically integrated quantum computing hardware company. So we build our own quantum control electronics, our own dilution refrigerators. We design and fab our own qubits, and of course, develop the software needed to control the computer. This allows us to seamlessly integrate the various subcomponents of the computer and gives us a unique perspective on the challenges and requirements to scaling up these systems. We also deliver our computers directly to clients as opposed to only providing cloud access. So most recently, we delivered a 24-qubit quantum computer to Compute Quebec, which is a high-performance computing center based in Montreal that provides supercomputing resources to academics, researchers, students in Canada. I'll leave it there.
Thanks, Jestin. Yoann?
So good afternoon, everyone. I am Yoann Jestin. I am the CEO and co-founder of K3 Photonics, a full-stack quantum networking company based in Montreal. K3 Photonics is providing hardware and software solution for the scalable deployment of quantum network within the current optical fiber infrastructure. So we are focusing on the scalability aspect, but also on the fact that we have to be as much compatible with the current telecommunication infrastructure. So we are using an integrated photonic platform for the scalable aspect, focusing on entanglement distribution between different nodes into the network. And yeah, we are combining scalability and high precision for the secure transit of information, but also for quantum sensing application, for example, or quantum information processing. So we really want to try to add the quantum capability to the current fiber existing network that we have already in place to communicate.
Thank you. Felix?
All right, I'm Felix Beaudoin. I'm the CEO of Nano Academic Technologies. So the pitch is like this. So every engineering sector, from aerospace to semiconductors, relies on CAD software, design software. Right? And this is used to predict technology performance before production. The problem is that most CAD software today does not contain the deeply quantum mechanical features that are needed to predict quantum hardware performance. Right? So this means that many quantum hardware companies still rely too much on trial and error, which means longer delays before practical quantum products are delivered. So at Nano Academic, we developed the CAD software that is needed for quantum hardware. We were spun out from McGill in 2007 as a computational materials science company. And in 2022, after growing organically for 15 years almost, we developed and released QT-CAD, which is the world's first finite element modeling software for spin qubits and semiconductors. And in 2025, we extended it to superconducting qubits as well. So this makes us able to model most of the world's solid-state qubits. So we have customers across academia and industry use cases. ST Microelectronics, Quobly, Quantum Motion, Equal One use our software. And yeah, that's pretty much the pitch.
Thanks, Felix. Paul?
Hello, my name is Paul Terry. I'm the CEO of Photonic. This is a Vancouver, BC-based company. We're currently about 160 people. We have subsidiaries in the US and the UK. We make spin qubits, which are photonically interconnected. 3 main markets. Number 1, quantum services, which we do with Microsoft. Number 2 is quantum supercomputers. And number 3 is quantum entanglement networks. Our goal in market number 1, quantum services, is to basically make quantum services available to the Fortune 10,000. That's our goal. And at the moment, we're on track to deploy something like 40 to 50,000 logical qubits in 2030. So we're on a mission to do that.
Thanks, Paul. And finally, Nick.
Good afternoon, everybody. My name is Nick Werstiuk. I'm the CEO of Quantum Valley Ideas Lab based in Waterloo, Ontario, Canada. So we're a not-for-profit applied industrial research lab focused on developing and commercializing quantum sensing technologies. So we look for interesting ideas that we can then take down the path and move towards a commercial-ready prototype, patenting along the way. And then once the technology is ready, we then create spin-out companies to commercialize that technology and take the products to market. We have four projects active. The first project is Rydberg Atom RF sensors for telecom and spectrum monitoring and defense use cases. We've spun that out to a company called Waverite Instruments, and they're growing and selling alpha product today for that capability. We have a derivative of that product for increase the sensitivity of it to drive it towards multi-static radar for weather and defense use cases, a quantum gyroscope and accelerometer project, and then a 2-photon cesium optical clock for timing and potential GPS-denied use cases.
Thanks, everyone. I know I feel very lucky to have you all here on this panel and hearing your view. So there are many aspects to deployment, and perhaps the foundational one is the question of logistics and the supply chain. So I'd be very interested to hear each of your opinions and your insight into where you sit in the supply chain for quantum technologies, or what parts of it you access, and what do we need to do to make sure that it's robust and capable of scaling up to really application scale. I'll start with Jestin, go down the row.
Yeah, so I mentioned it in the introduction, but we've obviously made the conscious decision to be far more vertically integrated than most superconducting qubit companies. I think it was certainly in part a strategic move from a supply chain standpoint. At the time, there weren't that many dilution refrigerator manufacturers, not a lot of people building control electronics that were customized for quantum systems. I do think moving forward, it gives us a pretty unique strategic position, especially because when we're looking at scaling up these systems, the electronics and the dilution refrigerators are also going to need to scale up. And so it gives us the unique opportunity to be involved in that space, and also it maybe simplifies the system engineering part of integrating all these systems together.
Thanks. Yoann?
So for us, we kind of see ourselves for now in the supply chain as an OEM, basically. So we are building devices that can be used, for example, by national labs, universities that are still kind of in the research and development phase. So this is how we kind of manage to generate revenue for now. And as I mentioned, so we are a quantum networking company. So trying to, let's say, focus now more on the networking aspect and saying, okay, now if you really need a network, we can build that network for you. So we are slowly transitioning from building individual components to now building those components, assembling everything together, and having solution like hardware plus software on top of it, to be kind of on top of the let's say the supply chain. So that's how we fit in that sense, and how to make it more robust. We kind of have strong collaboration with partners, also with governments. So yeah, that's how it works for us.
Thanks. Felix?
So I think we have a very well-defined part, contribution to the supply chain. We're an enabling technology, a little bit like fridges are another enabling technology. We're at the level of the design, so it's increasingly needed to use CAD software to reduce trial and error. Before we came in, there were, especially in spin qubits and semiconductors, strong needs. So people told us they were trying to use conventional CAD software from the semiconductor industry, and the outcomes were like convergence was difficult at low temperatures. There were missing quantum mechanical features, so we had to develop that internally. Now we're seeing it playing an increasing role in helping companies get a better sense of how their devices are going to work before they're fabricated. And in some sense, you could imagine doing it without it, just like in the, I don't know, early 20th century, people were building planes without CAD, right? But nowadays, you couldn't imagine that. This is a key component of all engineering sectors. So we think the same evolution will happen in quantum.
Thanks. Paul?
I think people over-index on the supply chain. I don't really think it's a problem. I think it's more of a tactical problem than a strategic problem. Most things that we can get almost anywhere. The only one that really is interesting is the quantum processors that we make. And that's only interesting from the perspective of sovereignty of nations when these processes go across borders. So this comes down to what is the world going to do when things move across different borders for different reasons, for political reasons, not for really any technical reasons, and whether a country wants its own sovereign supply of semiconductor chips. That's really the only supply chain issue I see.
Thanks, Paul. And Nick?
So we develop towards a TRL 6.7, what I'll call commercial-ready prototype of the system. So if we take the RF sensing and radar system, it's got kind of 3 Lego blocks in it. It's got the sensor, the control system with the lasers and the processing elements, and then it's got FPGA-based signal processing. So those 3 components are really come together to the solution. So if we look at each one, the easiest one, let's call it, at least from a supply chain, is the control unit. Assuming we get the right supply chains from the laser and the FPGA companies and things like that, that's mostly a COTS, commercial off-the-shelf assembly problem. The issue there is more every species that we use in all these different solutions in quantum has unique laser requirements. So really getting something that gets a volume of low swap kind of lasers that we can use to sort of continue to focus on the swap, see the size, weight, and power and cost of those solutions. The sensors are really a secret sauce item for us. We've invested heavily in the ability to manufacture and fabricate these sensors, have a bunch of IP and patents and trade secrets on those. So that's a supply chain that we believe we want to have some control over and not something that we would farm out to somebody. And hopefully that's something we could supply through commercialization, through another spin out or what have you to more of the market. And just last one, the FPGA programmers, hard to find enough of them, but that I think is a pretty standard sort of supply item across multiple industries.
Thanks, everyone. I think the next part we could talk about is market strategy and adaptability. And to break things up a little bit, I have a question for the full stack quantum computing companies, Jestin and Paul. How do you approach balancing internal priorities and direction versus responding to a changing market? Maybe Jestin, do you want to go first? Or do you want Paul? Paul, yeah. Paul, please.
Okay, so first of all, we don't sell quantum computers to anybody. So we provide quantum computing services to everybody. So the market is really a cloud market. We've learned nothing over the last 20 years. It is, you don't need to own the hardware. You can actually sort of use it as a service. So that opens up the Fortune 10,000 to you, not the Fortune 100 that can only afford to buy a quantum computer. Idea number one. Idea number two is that the industry is changing so quickly that you don't want your depreciation of equipment can be so fast that you actually want to keep the technology pace going. So we own and operate all of our own equipment, and we just keep upgrading it so people don't actually see it. Idea number two. And idea number three would be, it's going to be an interesting question for government what they do in terms of allowing the market to access a quantum computer. There's so much power going on there. Do you want any way to access any service at any time? And that's a national security threat. So we haven't seen governments actually step up yet and go, oh, we should probably regulate the access to quantum services, but that's something I anticipate in the next 2 years.
Thank you, Paul. Justin?
Yeah, maybe something I'll add on our side is that we've seen that there's, from the market standpoint, there has to be a fairly important collaborative effort between our clients and ourselves to really engage people to use these computers, to get interested. Their feedback on it is also very valuable. So that's kind of an interesting, even after the machine's delivered, there's a lot of work there. And I think we've seen that from a lot of other companies. I know IBM's done a very good job at fostering an ecosystem around their machines. And I think that's something that's going to have to keep going moving forward. Yeah.
Thanks. And then for the other three of you who develop products, the question I have is, how do you balance pushing the market where it needs to be, solving problems that your clients maybe don't even know they have, versus responding to what the market is asking you for. And we'll go reverse order again, starting with Nick.
Okay. Yeah, I think, so sensing's an interesting market because sensing is not one market, it's 100 little markets. And so, you know, the sensing market that each of the companies might play into is really defined by kind of essentially a current market today where people use some of these technologies, right? Like I always say this, you know, people buy gyroscopes today. If we make a better quantum gyroscope that has a better price performance characteristics, people would buy that, right? People buy lots of antennas today. If we make a quantum RF sensor that can potentially replace some of those antenna use cases, then the market's kind of there, right? What we have to do from a technology perspective is show better, right, from the sensors that we're making. And I think getting to better requires you to have a fully working system and then have a system that you can then spend some time characterizing to post numbers that people can then understand in the markets that you're playing into. So there's always this tension between what, you know, like I kind of talk about market down, technology up, and we're always kind of in a bit of this cycle where we say, you know, which specific, let's say, RF market would value some of these technical capabilities, can we prove them, then explore with somebody what that is, and then iterate to say, you know, we need to do this to the technology to improve it to meet those market needs. But we always have to think of this kind of classical as is and the quantum 2B and show the market that what we're doing is better in some dimension. And better is not just about performance, better could be lots of different things.
Thank you. Felix?
That's a very good question, actually. So the whole idea of developing CAD software for quantum came from a professor 5-6 years ago. At that time, it was very clear that people would need that, but there was not really a big market. So we took a market risk, actually. So we didn't go crazy the first year. We had just a handful of people, like just a few people working on this project, leveraging government grants mostly, and we started slow. Eventually, once we had our first users, beta testers, we could see that we were on the right track, and we saw increasing amount of companies in our field popping up, and we could approach them, and really like building based on user feedback started to make sense. But at the same time, we didn't want to become the slaves of this user feedback because we have to see in the future and develop features that we know our customers are going to need and have them ready when they need it. So it's always this fine tension that you're right to call that a tension because you want to do both, right? You want to, if you only like believe in yourself and develop grand idea stuff, it's probably going to fail. But if you also only listen to your customers, you might not even build the product in the first place. So it's interesting. Over time, we built confidence that we are able to predict what's going to go next. And in fact, now sometimes we develop something. It's not so obvious that the users are there, but a couple of months later, guess what? Suddenly, they are all asking us about it. So it's an interesting game to play, I would say.
Thank you. And Yoann?
So yeah, for the market in quantum networking, it's kind of a very interesting market because we kind of can focus on the security aspect. For example, QKD applications. There is now also the aspect of quantum sensing that is growing more and more for distributed sensing application. And then after the next step also is going to be the distributed quantum computing. So for us, it's really trying to build the backbone of the network in order to serve all those kind of different markets. And I think it's important also now for us, it's time to have some use cases development. And this is the kind of thing that we are doing with National Research Council of Canada, for example. So they are working on the sensing and metrology part, and we are kind of building a small network for them. So it's going to be very important for us also to demonstrate that with the network that we have been able to build, we can show application in quantum sensing. Now we are also looking into application into security, trying to go beyond quantum key distribution application, like for example, multi-party computing application and stuff like this. So really trying to move away from the point-to-point communication that we had before to multi-party applications. So really talking about network where there were different people that connected to the network, like basically the quantum internet. So yeah, that's basically where the market is.
So as Felix pointed out, a lot of these technologies have come out of academic labs. And when you go to deployment, the problems you face aren't just logistical or market needs. There's still the science and engineering never stops. So I'm curious to hear from you all, what are the challenges in the engineering and science domains that you've faced that are perhaps unique to attempting to deploy at scale versus purely an academic problem? And Jestin, do you mind kicking us off?
Sure, yeah. So in the superconducting qubit world, I think that there's kind of two aspects going on simultaneously. I think there's a lot of interesting research in building better qubits. I think if you look at the backbone of most deployed computers, we're using transmon qubits, which are kind of the simplest possible superconducting qubit you can come up with. And so there's a lot of interesting research in the benefit of the superconducting world is that you can engineer your own qubits. And so there's a lot of interesting stuff in building better qubits. But I think on the engineering side, there's also a lot of work that needs to be done in scaling up these systems. So whether you're talking on the QPU side and the 3D packaging and integration to get the IOs there, on the dilution refrigerator side, it's getting the how do you package the IOs, you cool them down, going down the cryostat, build cryostats with enough cooling power, size. The control electronics are, I think, often something that's not talked about, but if you look at the cost of these systems, it's a huge part of the cost is the RF electronics. And so, if you're talking about going to thousands to millions of qubits, the cost of the electronics to run this thing would be tremendous. And so there's a lot of work there as well. So yeah, some interesting challenges.
So lots of them.
Yeah.
Yeah. Yoann?
So yeah, it touches a lot of points actually. So we were at K3 Photonics experts in photonics. And then we realized that if we want to have a scalable product, if we want to make them compact, also, we're going to have to integrate with a lot of other things. So we quickly realized that we need a lot of expertise in electronics, for example. Nick was talking about FPGA. So we have learned a lot during the last years about how to program this FPGA stuff. So integrated optics, it's great. It's small. It's compact. But there's all the electronics that is around that actually make things bigger. So we're also working on that. On the mechanical aspect also, it's pretty important to have something robust, especially if you work with the defense, for example. They want to deploy that on the field. So I remember one of the first packages, one of the first device that we sent using one of the transporter. It arrived in US completely destroyed. So we learned a lot from that. And so yeah, now on the mechanical aspect, this is something completely different that we have now. But yeah, it touches a lot of domains, actually. So not only photonics we are able to do it, but yeah, electronics, mechanics, and design the system to make it reproducible. That is pretty important.
Seems like a lot of trial by error to find the problems that you face.
Exactly.
Yep.
Yeah.
Felix?
So to answer this question, I think I'll break it down into 3 items. So the first one is solving the right problems. The second one is solving them the right way. And the third one is distributing solutions to everyone. Right? So solving the right problems is essentially handled by academia. So there are hundreds of excellent papers in the literature that tell you how you should model this and that system. There are validations that have been done by experimental group already. So you can build on that. Like, solving them the right way is where I think companies become very useful. In the sense you have to do this efficiently. So typically a user will not bother using your software. It takes them like more than a couple of hours to get a solution because he wants to sweep parameters, optimize. So anything that's well above an hour, forget it. So you have to really optimize there. And then there is innovation that's typically at the algorithmic level There's some of it in academia, of course, but in industry, that's really where we shine, I think. We have to really focus on this. The third is getting the solution accessible to everyone. It's not enough to solve it on your laptop. It has to be accessible on all OSs. Everybody has to be able to run it, or it's have to be available in the cloud, but you have to find a solution so that everybody can run it, right? And that's more of a software engineering, packaging part of the job. It's not necessarily the sexiest part, but it has to be done, and it's important to put the right amount of resources there. And there's some trial and error involved, but at the end of the day, if you do it right, it works, and everybody's happy. But I would say like items number 2 and 3, that's really where the industry's role is.
Thanks, insightful answer. Paul?
Okay, this is a 1-hour answer. You ready? So I spent 20 years building the world's wide area networks and another 10 years building supercomputers. And first of all, people don't understand what scale means. So scale, my definition of scale would be the marginal cost of adding one more thing should be 0. If it's not, then you can actually make a big thing, but it doesn't scale. Point number 1. Point number 2 is everything you deploy has to be subject to a service level agreement, everything. And so what is that service level agreement? What is your mean uptime? What's your mean time between failures? How often will they fail? What is the customer success rates? What is the 5 nines reliability that you need actually on the machines themselves? And so when you engineer, you have to engineer to that. I, for one, don't think quantum computers are actually very complicated to engineer. So you can engineer them. They're not very complicated machines practically, but you have to engineer them to scale. It is true that some of the components like cryostats and so forth are engineered for lab environments, not commercial environments. Those things will need to change over time, but it's actually not rocket science, oddly enough. And so having a service level agreement, meeting a service level agreement, even little things like having enough space around the computers to be able to own, operate, and maintain the computers is very important. And then your question is about redundancy, and redundancy is probably the biggest issue that we solved when we did the big supercomputers. How do you maintain a program running for 2 months and it can never fail? And so those are the tricky engineering questions. These aren't quantum questions, these aren't physics questions, these are standard telecom / data center questions that have been answered in the past.
Thanks, Paul. And Nick?
So I think from where we sit, the problems, so what we're seeing is this pressure to prove things and prove things in close to real world environments. So the market's shifting quickly, or shifted quickly towards show me, your prototype, take it to a test location, and make sure I can actually do things with it. And so this stuff of like the science of it on the back end in the lab is great, but take what you've got in the lab off the table faster and package it into something usable. And so that's the cycle we're in. And so, as we look at our staffing of, a mix of physicists and maybe some engineers and things like that, we're starting to think more about, even in a TRL 3 to 7 lab, thinking about more productization expertise in-house to help us kind of think about some of those design for product issues earlier in the cycle, so that we can take these prototypes to a point that they can actually be proven and we can post the numbers that people want to see, so that they can do the bake-off in their mind about the classical stuff that they're using today and see that this quantum capability is promising and is better in some dimensions. And so we've started to think a lot more about that problem than the further, the deeper science problems. We're still going to work on the science to innovate and think of new things, but we have to increase investment and increase focus on provability of the technology. I think the market is expecting that now. I think there's been a lot of money spent on the fundamental research. Now the money needs to be spent on application of that research into capabilities that matter for different markets, commercial and defense.
Thank you. So we have about a minute left. So I first would actually just want to thank all the panelists for all these insightful answers. I certainly feel like I learned a lot, and this was a very rewarding experience. I hope you all in the audience do as well. In this last minute, maybe with just a show of hands or a vote, I'm going to ask a little bit of a controversial question that came out of our discussions leading up to this panel. Is scaling quantum technologies to deployment, is that an engineering problem or a science problem? And maybe I'll just do a vote. Who says it's a science problem? Please feel free to vote in the audience as well.
Is quantum a science
Is scaling quantum technologies a science problem? Is it an engineering problem?
Can it be both?
Is it both? Ah.
It's a boring answer, but I think it's both.
Yeah.
No, it's
Well,
not an engineering problem.
on that note, thank you again to the panelists. Thank you all in the audience for listening. I hope that you enjoyed it as much as I did. And enjoy the rest of your time at the Quantum World Congress. Thank you.